Hello, I'm happy to meet you all. I hope we can talk to each other in classroom soon. These three books are what I can find in China, and I believe they are good for this course. If you have any opinion about textbook, please don't hesitate to let me know. Let's talk about the objectives of this course. 1. You engineering majors need to understand the laws that govern the nature. Second, you have studied physics in high school, which is based on algebra. It is not enough for you to solve engineering problems. Now, you are studying advanced mathematics like calculus, probability and statistics, complex variable functions, etc. You need to use your math in this physics course. Third, as an engineering student, you should focus yourself on your specialty, but physics courses give you a much broader knowledge vision. So, you may find someday physics is so beneficial to your career. In your childhood, you want to understand the world, right? You may ask your mother, why am I here? Even the earliest human beings had asked themselves the questions, why is the universe organized the way that it is? And these questions are what we attempt to answer in the field of physics. Now, you've grown up, and you have studied mathematics. Physics really does try to use mathematics along with some core ideas to explain the phenomena or the phenomena of the universe. Yet, physics is the foundation for all the other sciences. When we think about chemistry, which is exactly interaction between atoms, those interactions are really physics-based interactions. So chemistry is actually laid down on the foundation of physics. And then, even when we think about ourselves, our bodies, even our consciousness, our brains, they are really all related to chemistry and physics. And we are going to see that more and more as we go into physics. All these complicated phenomena that you see around us, whether you are looking at a galaxy or we are looking at ocean waves, or we are looking at even biological systems, we'll see that an amount of them can start to be described using some fairly simple physics formula or equations. The more you approach the engineering practice, the more complicated you find the problem to be. Let's take a look at these so-called static systems. For some network of pipes or bridge or tracks, nothing is moving in these systems. So you will be asked to find the force or torque at various locations within the systems. So you can see what one beam feels, in which way it wants to move. A dynamic system is moving. Examples of problems will be like some complex pendulum that swings back and forth, or a transmission system that consists of some gears rotating about different axes. Some system has a lot of moving components, This problem specifically asks you to determine the center of mass, rotational inertia, the maximum angular acceleration, and so on. Solving these problems involves plenty of math, vectors, calculus, etc. You need to learn about Lagrange's and Hamilton's equations, which give you a lot of power in terms of representing complex systems. If you are given a problem in which a mass slides down a circular wedge, for students who have some basic physics knowledge, this may seem easy. But in this problem, there is no friction on the wedge in the ground. And you are asked to find the equation of motion for the mass and the wedge itself. Please note below the diagrams is the answer, by the way, to emphasize the complexity compared to what you may think. How physics courses help engineers? Well, generally speaking, the obligation of scientists is to find something new in nature. The point for science is discovery. Scientists contribute knowledge to society. The duty of engineers, on the other hand, is to create something new that does not exist in nature. The keyword for engineering is creation. Engineers deliver products to society. So, how do physics courses help you engineering major students? Honestly, engineers use physics on top of engineering principles to solve problems. Here is the job for engineers. Civil engineers have interests in designing bridges, tunnels, dams, roads, buildings that can stand up to earthquake, etc. Mechanical engineers build cars including the engine structure, suspension, and braking. They maintain a proper temperature within a spacecraft. They help make the wind turbines aerodynamic and highly efficient. They design aircrafts, robots, biomedical equipment, and so on. Electrical engineers can help improve the efficiency and speed of electronic systems like those in your cell phone and computer, all the way to those in satellites. You could work on wireless communications and ensure that two satellites can communicate with each other securely, or you could help improve the coverage for a cell phone company. You can work for power plants, renewable energy technologies, and more. Computer science majors who are going to titled as software engineers write software, build control systems, develop ways to help the environment design, medical tools, and plenty more. Aerospace engineers can work on the structural design of an aircraft or spacecraft and test the propulsion system, ensure that the aircraft is capable of traveling at supersonic speeds, make an analysis of the aerodynamics, and so on. Chemical engineers work on the process that makes the fuel engines, medicines, solar panels, computer chips, rocket fuel, and so much more. chemical engineers also work on chemical reaction control systems, safety systems, and environment protection systems. Well, what physicists do can be of any help. I would like to name a couple of good news. I'm not sure if you have ever heard of plasma physics. An actual physicist or cosmologist may study black holes, galaxies, supernovas, dark energy, and why the universe is accelerating forever, etc. Most of the cosmological bodies are composed of plasma. Plasma physics may work on the fusion energy, which is the process that powers stars like the Sun, which we want to use here on Earth to power our home and businesses. A very common but not well understood phenomenon that exists in the universe is something called magnetic reconnection. When magnetic field lines within a plasma break, they quickly reconnect. This causes the solar flares. Princeton University has been conducting magnetic reconnecting experiments under lab conditions. Maybe someday they'll tell us how to make use of this phenomena in engineering. Condensed metaphysics is a huge branch of physics. One of the research areas deals with superconductors. That is, a conductor has no electrical resistance. This phenomenon currently only exists at very cold temperatures. But we can create ones working in room temperature. There will be countless applications for that, including faster computers, very accurate sensors, all the way to cars that can hover above the ground. Another specific area of condensed matter is Spintronics, which is about manipulating electron spin in order to produce certain results. Because electrons are charged, and the spin gives electrons properties of magnets. Current research is mostly about using that spin as a carrier of information, so we can represent data by the direction of that spin of electrons instead of physically moving charge or current. This research will lead to tremendous enhancement of electronic memory and reducing power consumption at the same time.